Hello, and welcome to part 1 of section 7.3. We will be computing volumes using the method of cylindrical shells. Now, the reason why this method is important is because we have problems like this one. So say, for example, say you want to compute the volume of the solid obtained by rotating the region bounded by y equals 2x squared minus x cubed and y equals 0 about the y-axis, okay? Now, if we do that, so let me draw that real quick. So this is my x and y-axis, and the graph of 2x squared minus x cubed, it looks something like this, okay? So this is y, this is y equals 2x squared minus x cubed, and then this is y equals 0. So this is y equals 0, and we're taking this area and we are rotating this area about the y-axis, okay, about the y-axis. Now if we do that, then the solid that we generate, it actually will look something like, okay, let me see if I can do this, it'll be something like that. So then you can argue, hey, look, I can just use the washer method, right? I can just use the washer method. Now the problem is that if we're using the washer method, notice that the thickness, notice that my integral will be given by dy, right? So we will have to compute this integral in terms of y. And this is where the problem starts to happen. Why? Because that means that then we have to take this function and we will have to solve for x so that we get a function of y, right? Because then again, my volume will be in terms of y. Okay, now I have no idea how to solve this function in terms of y, so we have to come up with another method, a different method. And this method, it's what we call the method of cylindrical shells, okay? So now, what is a cylindrical shell? Well, a cylindrical shell is something that looks like this, okay? So see, understand what's happening here. What's happening here is that we have something that looks actually like the washer thing, right? It's like we had this cylinder, this solid cylinder to begin with, and then we removed like an inner cylinder, okay? That's it. That's what a cylindrical shell is, okay? So now let me define a couple of things. So let me start by defining the letter R as the average of R1 and R2, where R2 represents the outer radius, so this is R2, and then R1 represents the inner radius, okay? Then I'm also saying that, well, delta R, as usual, it will define the difference in R2 and R1, okay? And then if this is the case, if we have that R is the average of R1 and R2, delta R is the difference of R2 and R1, then if on top of that, I here quickly define H as the height of the cylinder, so this right here is H, then the volume of my cylindrical shell is given by 2 pi RH delta R. That we have to prove, okay? So one more time, volume of the cylindrical shell is 2 pi RH delta R. Okay, so let's prove this real quick. So since we're using R1 for the inner radius and R2 for the outer radius, I'm going to call V1 the volume of the inner cylinder, and then V2, it's the volume of the outer cylinder, okay? So the whole thing. So if I take the difference of those two, if I take the difference of the volume of the outer cylinder and the volume of the inner cylinder, then you get the volume of the shell, okay? Does that make sense? You get the volume of the shell, okay? Perfect. Now V2 minus V1, well, volume of a cylinder is it's just pi R squared H. So pi R2 squared H minus the volume of the inner cylinder, pi R1 squared H. It's equal to, let me take pi H out, so I get R2 squared minus R1 squared. This is just the difference of two squares. So I get R2 plus R1 times R2 minus R1, I noticed that we defined R as the average of R1 and R2. So if I multiply by 2, I get R2 plus R1. So this is just 2R. And then by definition, R2 minus R1 is just delta R. So that's how we get that volume of the cylindrical shell is just pi H2R delta R, okay? It's in different order. So in other words, volume is equal to, well, circumference, which is just 2 pi R, height, which is H, and then the thickness, which is as usual given by delta R, which in this case, right, if you take here this thickness, this is delta R, okay? Perfect. So now how can I use this idea to find the volume of more general solids? Well, imagine that this is the graph of f of x, okay? So say this is the graph of f of x, and take some arbitrary here, some xi, then the height will be f of xi, okay? Now take that curve and rotate it about the y-axis, okay? Then we'll get something that looks like this, okay? There will be some empty space here, okay? Perfect. So now we want to find the volume of the little shells, okay? Find the volume of little shells. Now, if we were doing this in calculus 1 and we were just computing the area under the curve, you would use Riemann sums, okay? And you would get some rectangles, and as usual, the more rectangles you get, the better the approximation is. Now take these little rectangles and rotate them about the y-axis, then this is how you get your shells. This is how you get the cylindrical shells. Now, of course, the more rectangles you have, the better the approximation. So say, for example, here, say I had this, and then I have another one, and then I have another one, and then I have another one. You see, like the more rectangles you have, the better the approximation is. So the same way we're approximating area here using rectangles, we can think of this as a three-dimensional figure, right? And use shells to approximate the volume. So then if I have more rectangles, then here I would have like another smaller shell, right? And then something that looks like that. So there's another one, and then here you would get another one, right? Here you would get another one, so and so on. So great at drawing shells, but you see what I'm saying, right? I hope it makes sense. Perfect. Okay. So what I'm saying is that now I am using the volume of my cylindrical shells to approximate the volume, okay? So now, of course, if we go back to here, the radius will be given by, so here, if here I have my arbitrary xi, right? Then here, this is, let me take like here, if this is xi, then that will be my radius, right? That's the radius of my cylindrical shell. And then not only that, but then the height of my cylindrical shell will also be given by my function evaluated at, right? My function evaluated at, so this will be f of xi, my function evaluated at xi, okay? So then volume is 2 pi xi, right? That will be the circumference. Then f of xi, that's just the height of my cylindrical shell, and then delta x, that'll represent the thickness, okay? Right? Delta x will represent the thickness of so this is my delta x, okay? Which is just here, the space between my rectangles, okay? So then again, notice that I'm doing this in terms of x. There's nothing to solve. We just take our function, okay? Perfect. Okay. So now, as usual, the more cylindrical shells I have, the better my approximation. So now imagine that you have infinitely many cylindrical shells, then you'll get the exact volume. So this is for this specific case where we are rotating the region bounded by y equals x, x equals a and x equals b about the y-axis, okay? So in this case in particular, think of our function being continuous on the first quadrant. We have that the function is positive, and then a and b are also positive, okay? Perfect. And this is what we get. So of course, this is just one case, right? We could be rotating our region about the x-axis, and then everything will be in terms, then the thickness will be given by dy, and then everything will be in terms of y. Or imagine if I take if I take the region and I rotate it about the line x equals 5, then you have to shift the function and we'll have to make some changes. But then it makes no sense to go over every single little case. I think it's more important to just understand what's going on. And what is going on is that volume is given by the integral from a to b, okay, a to b, of the circumference times the height times the thickness, and then again, the height is the function evaluated at, say, for example, x or y, and then the thickness is either dx or dy, okay? Perfect. Stay tuned. Watch part 2. Bye-bye.